Question 2 from the 2018 Advanced Higher Physics Examination. A student places a radial-controlled car on a horizontal circular track as shown in figure 2a. The car travels around the track with a constant speed of 3.5 metres per second. The track has a radius of 1.8 metres. And for 1 mark, we're asked to explain why the car is accelerating, even though it is travelling at a constant speed. Yeah, here we go then. We take a look at the overhead view of what's happening. This circular white circle represents the track, the dotted lines represent radii of the track, and the black lines represent the velocity vectors of the car at 2 different times very close together. Now, as you can see, the size of these vectors are the same, but the direction of them changes. And the key thing here for this 1 mark is to state the following facts. A vector has both magnitude and direction. Now, if we change either magnitude or direction, or both, that means there's a change in the vector. And if there's a change in the velocity vector, in this case its magnitude is staying the same but its direction is not, then we have a change in that actual velocity vector. And a change in a velocity vector will equal an acceleration. So the car is actually accelerating due to the fact that its velocity vector, even though its magnitude is staying the same size, its direction is changing. So that would be an answer for that, simply for 1 mark. But let's delve a little bit deeper into where the acceleration is pointing to. Now, this is not part of the mark for this question 2, but it's just a wee bit of background information just in case it would actually appear again in future exams. The diagram you're looking at there, you can see the velocity VA represents the velocity of the small radial control car at a particular point in time. A fraction of a second later, at this position here, the velocity will be VB. It has changed, as we've just discussed, because its direction has changed. Its magnitude has not changed. Now, where is in fact acceleration? Well, we know that acceleration is equal to change in velocity. So we can write down what the change in velocity is. Now, therefore, we'd have to put down what delta V is. And delta V is going to equal to the velocity at B, the vector velocity at B, take away the vector velocity at A. Now, let's look at this diagrammatically and see what is happening. Here we have the velocity vector VB. It matches up there. And here we have the velocity vector A, which matches up there, and both are the same magnitude. Now, in that position there, VB and VA cannot be added together in this form here. We have to take the negative of VA, and the negative of the vector VA is just simply one pointing in the opposite direction, like that, with the same magnitude, same size. Now we can add nose to tail. So we do this one here, VB, and put the tail of vector minus VA onto the nose of VB, we have the proper sum, VB minus VA. And what's the resultant in that? The resultant will be from here, VB minus VA. Now, if we reduce that time between the two parts of the motion here, then obviously this little vector here will become more and more near the middle of the 2 points we're measuring, and look at its direction. It's going towards the centre of the circle. So that little proof shows you that the acceleration of this little car is actually pointed towards the centre of the circle. That is the centripetal acceleration. So to recap that again, remember this is just a wee bit extra explanation. For your 1 mark, all you have to say is that a vector has both magnitude and direction. Velocity will have a magnitude and direction, and even though in a circular motion the magnitude, the speed of the velocity vector remains the same, its direction is changing, and that constitutes a change in the velocity, and a change in velocity means an acceleration. And that little proof I just showed you there shows that the acceleration is pointing towards the centre of the circle. Question 2a, part 2. Calculate the radial acceleration of the car. Well, we know from our data book that the radial acceleration of the car, AR, is going to equal to the velocity squared divided by the radius of the circle which is going round them. So we've got all the data we have there, so we can just put in the numbers. The velocity, the tangential velocity is going to be 3.5 meters per second all squared, divided by the radius, which is going to be 1.8. And if we do that on our calculator, we end up with a value of 6.8 meters per second to the minus 2. The key point here being that the radial acceleration is acceleration which is pointing into the circle, which we described in the last question, and that's going to be v squared divided by r, and we can work out the numerical value for the question, 6.8 meters per second every second. Question 2a continued, part 3. The car has a mass of 0.431 kilograms, and the student now increases the speed of the car to 5.5 meters per second. The total radial friction between the car and the track has a maximum value of 6.4 newtons. And we have to show by calculation for our 3 marks that the car cannot continue to travel in a circular path. So what keeps the car in a circular path? Well, it is the frictional force, the radial frictional force between the car tyres and the track. And it's that frictional force which gives rise to the centripetal force. And that's very important to remember. It is the frictional force that gives rise to the centripetal force. That's the force keeping the car going round in a circle. And looking up our data book, we know that the centripetal force, F, is given by the following: the mass of the object, the tangential velocity it has, v squared, divided by the radius of the circle which it is prescribing, the radius of the track. So we've got all that data to look at, and we just put the data in. F equals the mass, which is going to be 0.431, multiplied by the speed of the car, which is now 5.5 meters per second, and we'll square that. Put a bracket on the top, and we're dividing that by the radius of the track, and the radius of the track is 1.8 meters. So we do that calculation, we end up with a value of 7.2 newtons. So that's the value of the centripetal force. But as you can see, the frictional force in fact is less than that. So the frictional force has a value of only 6.4 newtons. Now therefore that's not enough to provide the required centripetal force to keep the car on the track. So 7.2 newtons is much bigger, therefore the car will go off the track, it will move off in a straight line from the track in that direction if you increase its speed. And that's what happens when you get something on a circular track and it's moving around. If you increase the speed, say it was Scalextrics, you'll find out the car goes off at a tangent. And the reason for this calculation is that we now know that giving that speed and that radius of track, the centripetal force required to keep it in a circle is 7.2 newtons, and we're only having a frictional force of 6.4 newtons. So therefore, that's far less than the force which is needed to keep it in the circle, and therefore the car will not continue to travel in a circular path. Question 2 continued, part B. The car is now placed on a track which includes a raised section, and this is shown in figure 2b. It's not drawn to scale. Now the raised section of the track can be considered as the arc of a circle, which has a radius r of 0.65 metres. And for 2 marks in part I, the car will lose contact with the raised section of the track if its speed is greater than Vmax. And we have to show that Vmax is given by the relationship Vmax equals the square root of gr, r being the radius of the track at that particular point, and g being the gravitational field strength on the surface of the road, of the planet, which is equal to 9.8 newtons per kilogram. Now let's take a look at a close look at what's happening to that car as it reaches the top of its track. Now there'll be 2 forces acting on the car. The first one is we know is going to be the weight of the car acting downwards, straight down like that. And the other force is due to the force of the car, the road pushing back up on the car, and that's the normal force, which is given the symbol N. So there's the 2 forces acting on that car. And if we resolve these 2 forces so that they act in a downward fashion, towards the centre of the circle, then we can get the centripetal force acting towards the centre of that circle. So resolve the two forces acting downwards, and that will give us the value of the centripetal force. And as the centripetal force acting downwards. I've not drawn them exactly in the same vector way, but you know the centripetal force will be the resultant of the force acting downwards towards the centre of the circle. So let's work that out in terms of algebra. The centripetal force, Fc we'll call it, F subscript C, is equal to the downward force of mg, take away the upward force of N. And that's really what our centripetal force will become, mg minus N. Now to lose contact with the road, N, the normal force, must become 0. The force is no longer pushing up on the car. So in this case, to lose contact, N must be equal to 0. The normal force must be equal to 0. So to lose contact, N must be equal to 0. So we now have a simple equation that the centripetal force will be equal to mg for this particular maximum speed, which will result in losing contact with the road, N equal to 0. So we know that Fc equals m v squared, and it's a maximum speed, we'll leave that out for the moment, divided by r, and that equals mg. So to find this maximum speed, we can see that the two m's cancel, and v squared becomes equal to g times r if we cross multiply. And therefore, this maximum speed, which we will write as mx, vmx, will be equal to the square root of g times r. So the whole idea of solving this problem is to resolve the forces towards the centre of the circle. That will be mg, take away n's acting upwards, we're looking downward towards the centre of the circle. And at a certain speed, if you lose contact, the normal force, which is the road pushing up in the car, will become 0. And that reduces our force equations to become the centripetal force equals mg. And we know the value of the centripetal force, we can write down mv squared upon r. That will equal mg, and a wee bit of algebra gives us that the maximum speed that car can go when it will lose contact with the road is given by the square root of g times r. Question part 2. Calculate the maximum speed Vmax at which the car can cross the raised section without losing contact with the track. So here's the situation. We have our maximum speed of the car without it losing contact, and we've got the radius of the track at that particular point, and we know from our previous derivation that the maximum speed which the car can achieve at the top of that road without losing contact is the square root of g times r. So that's going to be the square root of 9.8 multiplied by the radius of the track, 0.65, and that will give us the square root of, if we do that on a calculator, to give us 6.37, and the square root of 6.37 comes out to be 2.5, and our units are metres per second, since that's the speed of the car. So the maximum speed that car can travel at without losing contact will be 2.5 metres per second. Question 2b continued, part 3. A second car with a smaller mass than the first car approaches the raised section at the same speed as calculated in B part 2. And we have to state whether the second car will lose contact with the track as it crosses the raised section. And we must justify our answer in terms of forces acting on the car. Well, if we go back and look at our condition for the car to keep on the track, it must have a speed less than a maximum speed equal to the square root of g times r. If the speed of the car is less than that, it will hold on to the track. If the speed of the car is greater than Vmax, it will leave the track because the normal force will be in fact reduced to 0. So in this situation, we see here that the maximum speed is really independent of the mass. It only depends on the radius of the track and g itself. So it doesn't matter what mass of car approaches that track, that kind of hump in the road. It only depends on the speed that it's going at. Mass is not involved. Now, otherwise, in the question it says, justify your answer in terms of forces acting on the car. Well, we could go down the line the following way. A smaller mass means a smaller centripetal force. And we know that because we've got the centripetal force equation, Fc is equal to mv squared upon r. So the radius of the track stays the same, the speed stays the same, but if you reduce the mass, you're going to have a smaller centripetal force, and that means there'll be a smaller force required to keep it in a circular path, and therefore it will stay on the path. But I would prefer to answer it in terms of this part here, where the maximum speed is really independent of the mass and only depends on the radius of the track and the value of g.